Good afternoon, everybody. Good to see it's the last paper to be presented. So today I'm going to introduce this work, AnyPro, the preference preserving Anycast optimization based on strategic ASPP prepending. Despite I'm doing machine learning stuff right now, I'm still very proud of this work because it really solved the problem without machine learning. So what is IP Anycast? IP Anycast announces the same IP prefix from multiple sites to all the clients, and so that the clients will be routed by BGP policies to the site that aligns with BGP policies. Many services use IP Anycast for like resilience first and for performance, that given even some sites are down, the user clients can still be routed to one of the POPs. Here, we use the POPs. It's a combination of a physical location and a transit. And both DNS, CDN, and DDoS mitigation uses IP Anycast. However, the large-scale deployment of IP Anycast have a challenge in steering the routing behaviors. On the left side, it is the ideal case that we want the clients to reach the closest sites for optimal cachements, like the lowest latency and the smaller geographical distances. However, the real case is usually on the right side, like clients might reach the faraway sites, leading to the latency to be very high. The challenge lies in that the BGP determines how it really goes. There can be from 5 to 30 hops in between. But BGP protocol itself is unanalyzable, to know that which hop in the middle is how it is making the decisions. And also it's performance agnostic, which means that it doesn't really want to make the optimization for you. So also, ideally, we want to scaling up the sites that the user can reach out to more options locally. However, we find this not the case because even if we have more than 20 POPs over the world, the user can still have a very inflated path that has over 120 milliseconds for RTT. There are some existing works. AnyOpt in 2021 construct the total preference order for all the Anycast for each client. It is doing a pairwise comparison. Like if we turn this down and turn A down and turn B off, we see that it goes to A. But if we turn it on together, it also goes A. It means that the client prefers A than B. And after doing the global pairwise comparison, we can finally choose a subset of site to be open. However, this way has a problem of underutilization of all the available site resources. And also, turning on and off is a very coarse granularity control that usually the business do not really want it. And the second type of work is original IP Anycast. Its philosophy is a combination of DNS-based method and the IP Anycast. It assigns multiple IP segments instead of just one, to each geographical region, so that it can avoid extreme path inflation from Asian to Europe or Asian to America. However, it increases the IP segment resource usage as well as reduces the global resilience, and the steering inside each region is still not optimal. Therefore, we want to have a fine granularity knob that can steer Anycast traffic globally and with minimal infrastructure change. That's the answer, ASPP prepending. ASPP prepending, short as ASPP, is a BGP mechanism that artificially increase the advertised path lengths. Suppose this route previously have 3 hops, but I can announce that at the first beginning I say that +3. Then when the client received it, it shows the path length is 3 + 3 = 6. It can make this route less preferred. And by strategically adjusting the prepending size, we can influence the global pattern or mapping of client to POP and steer the traffic. Here's the case. Suppose we have like 2 IP, client IP and 3 POPs, and there is an undesired, unpreferred mapping. And then we can prepend Frankfurt so that the run client IP from Ashburn can avoid going to Frankfurt and choose Ashburn instead. And if we prepend Paris, the run client IP from Frankfurt may also go to the correct POP in Frankfurt. However, for a global stuff, we know there can be conflicts that 2 clients who their preference cannot be satisfied simultaneously. Like if an Ashburn user wanted the Frankfurt to prepend, but a Frankfurt user might want the Ashburn to prepend, then it will go into a hard conflict. So what's the optimal mapping of the IP Anycast cachements? To achieve that, let's formulate this problem as to maximize the mapping between the preferred and the actual mapping. Here, the C is a client and P is a POP. And we want to maximize the correlation between these 2 mappings. And for actual mapping M here, the one client can only connect it to one site at once. But for preferred mapping, maybe you can choose like for the same area or like geographical distance less than 800 kilometers, or like the measured RT is less than 60 millimeters, etc. So you can do whatever the preference. And the partial order preferences are defined that given the configuration S, the client CK will choose PIJ instead of PMN. Or in that case, we define that the preferred mapping value must be, the MCK PIJ must be larger than MCK PMN. So this is a reflection of the partial order preferences. However, the challenge here is that it is computational complexity very high because the ASPP configuration can be like 10 times 20. So the search space is very large, and we want to have a way that infers sufficient routing topology context instead of exploring all the configuration space, and also minimizing the total number of required configuration experiments. So this problem can be formulated as a weighted max satisfaction problem, and explore like, for each client, it requires some of the inequations, we call it constraints, to be satisfied. Like the Frankfurt user want the Frankfurt lens to be 3 less than the Ashburn, etc. So that we are trying to satisfy as many as possible from these constraints. So AnyPro is designed with this formulation that we, apart from the production IP segment in the top right hand, we have an IP segment for testing instead, but using exactly the same infrastructure from the company. But this IP segment is not used purely for probing and testing purposes. And for each POP, we have a prober and the listener. The prober sends out a ICMP request, and the listener will detect which client reaches which POP. And in this way, we can collect the ICMP responses from all the users, say that 240K users, and know that what's the real catchment mapping goes like. And then we use the max-min pooling to discover all the clients that are sensitive to ASPP prepending config changes, and then reveal what's their constraints that they want to go to their preferred locations. And for handle these contradictions among constraints, we iteratively run the measure, tuning, and optimization to tighten the constraints step by step until the contradiction has been solved, or like we know that it cannot be solved. For max-min pooling, we first starting with setting the prepending size to max for all these cases. All max is equivalent to all 0, and it looks like this for all max. And then we grab each pop and then make it to 0. In this case, this pop will be the most attractive pop among all these ingresses. And in that case, if any a client reaches this pop, we know that this pop has the attraction to these client IPs. And for instance, when we turn Ashburn to 0, we can see that this Ashburn client goes to Ashburn. And then we know that this client IP requires the path length of Ashburn to be less than path length of Frankfurt minus max. Yeah, this is the core preliminary, one of the preliminary constraints. And then we return it to all max again. And then for step 3, we do Frankfurt equals 0 so that we can see which IP are sensitive to Frankfurt and then have their preliminary preferences. And after gathering all these preferences, the complexity is just ON. And we have proved that the max-min pooling is complete for finding all these ASPP sensitive clients. And the next step is to resolve the contradictions. It is an iterative methodology. And for each contradicted constraint pairs, we conduct a binary scan to find out that if each of them can be tightened by half, and so that they can be satisfied simultaneously. If not, it will search into the half with signals. Here is an example, like if a client requires ASPP prepending 1 to be larger than ASPP prepending 2 plus 9, and 2 requires to be 9 larger than 3. This is a contradiction, which means that in any case, we cannot satisfy them simultaneously. If we make 2 equals to 0, then the second one cannot be satisfied. So after the binary scan, we can find this resolution that to tighten these parameters in this configuration to be 4 and 5, so that in that case, we can find out a config like ASPP 1 equals 9, 2 equals 5, and 3 equals 0 to satisfy these two clients to be reach their optimal size simultaneously. And we start to look into how AnyOpt benefit the RTT, and as well as the objective defined in the optimization problem. From the 90% percentile, we can see that if we leave the prepending all 0, the round trip time is 271 millimeters. And for AnyOpt that strategically turns on and off the sites, the 90% RTT is 87 millimeters, and AnyPro achieves 58, which increases handles the long tail are inflated paths successfully. And also, if we look into the definition in the optimization problem, we can see that the preference, our alignment has been increased, like previously to be only 68% of all the clients can be satisfied, but we can make it to reach 0.85 as the skyline. And Here has a scaling such that in case the system is extremely large, that has more than thousands of POPs, despite not really practical in the modern internet. This exploration can have a longer time, and in this way we can have an early stop that maximizes these high weight clients first, and then also have a good result. But in our experiments with only 20 POPs, we can always finish the skyline optimization. The computation is within like 100 milliseconds. Also, with and without pairing, we can see that the improvement is both significant. And AnyPro is orthogonal to AnyOpt and regional IP Anycast, because like AnyOpt select POPs to turn on and off, and AnyPro refines the ASPP settings. They can be combined and performs better than AnyOpt, and handles both with pairing and without pairing scenarios. And next, we want to see that whether the theoretical formulation of the preference, which is defined as normalized objectives as M, aligns with RTT. So we define the objective as the geographically closest site, and then analyzes the Pearson correlation between RTT and normalized objective, and 95% RTT with normalized objectives. We can see that it has more 0.95 Pearson correlation for the first graph, and 0.96 correlation with the second graph. And then for the normalized objective not only for global, but also we trying to align with the original IP Anycast settings, which only optimizes for a subset. In this set, we choose the Southeast Asian as a subset, and we find that no matter what the scale is, the AnyOpt can both improve the normalized objective, but the smaller the fewer the POPs are, the better the performance would be, because the unwanted contradictions would be few. But in all these cases, the normalized objective is more than 80%, which is a significant improvement than the previous methods. And we also, to be sure, we also tried several machine learning-based methods like classic decision tree and the deep neural networks. But without this kind of context of BGP, the performance is worse even with more than 1,000 exploration traces. Yeah, that's it. That's our work. I'm happy to take any questions.